You see a page of notes you need to remember, and you instinctively pull out your phone to snap a quick photograph. The camera lens does exactly what it's built to do. It faithfully captures the physical reality in front of it. But when you're trying to preserve a document, physical reality is precisely the problem. First, there's perspective distortion. The top of the page ends up looking narrower than the bottom, warping the text. Then there's lighting. Your body casts uneven shadows across the center of the page, burying the ink in darkness. And finally, a modern 12-megapixel photo wastes millions of data points memorizing useless information, like the grain of the wood desk or the exact shade of the ambient light in the room. To actually digitize a document, we need the mechanical precision of a bulky flatbed scanner, but we have to build that machine entirely out of software. The first step in this digital assembly line is edge detection. The software has to figure out where the paper ends and the messy real world begins. The algorithm scans the image for sharp, high-contrast boundaries, snapping a digital wireframe around the page perimeter. But it must ignore false edges, actively steering around visual noise, like a notebook spiral binding, to map the true edge. Once those four corners are locked in, the software applies a mathematical translation known as a homography matrix. This matrix calculates exactly how to stretch, pull, and warp that angled trapezoid shape until it forms a perfectly flat two-dimensional rectangle. Through pure mathematics, the software neutralizes the physical angle of the camera lens, handing us a perfectly flat canvas. But we still have a massive lighting problem. In a raw photograph, a heavy shadow falling across a page can read as the exact same color as blue ink resting in direct sunlight. Standard photo editing fails here. If you simply crank up the overall brightness of the image, you end up washing out the lighter text in the sunlit areas. The solution is a process called adaptive thresholding. The computer stops looking at the photograph as a whole and begins interrogating the image on a microscopic level. It evaluates a single pixel by comparing it to its immediate neighbors. The rule is binary. If noticeably darker than local neighbors, it's classified as ink and turns black. If similar, it's classified as paper and turns white. Looking at this technical sketch of a piston, we can see the macro result of millions of these tiny decisions. The detailed pen strokes and Persian annotations remain perfectly intact and legible, pulled from deep shadows without losing a single line. By shifting from a global view of the page to a localized one, the software successfully extracts the human intent, the actual ink, from the interference of the physical environment. There is one last layer of physical residue left to handle: the texture of the paper itself, or the pre-printed lines of a notebook. Secondary background